to explore these types of waves for the next several days, but this is your introduction into mechanical versus electromagnetic. So we're going to begin with mechanical waves. Before we start, go ahead and write mechanical versus electromagnetic across the top of your paper. Mechanical waves are going to require a medium. The best example is sound waves. If I were to turn on a stereo and begin playing music, we can hear that because the sound waves leave the stereo, travel through a medium, the air in the room, and arrive at your ears. However, if we were to remove all of the air from the room, we would be unable to hear that sound. Even if the stereo is playing, the sound waves would not have a medium to travel through to get to your ears. There are three different types of mechanical waves. The first one is going to be called transverse. A transverse wave is going to move in an up and down motion, often looks like hills and valleys, and it's going to be oscillating perpendicular to the propagation. There are several words in here that are like, what is that? So the first one is oscillates. Oscillate's just going to mean that it's moving back and forth. That might mean up and down like hills and valleys like we see in transverse, but we might see that word again in a moment. Perpendicular, we know. We've heard this word in math before. We know that this would look like parallel. So if this were my direction of motion, if it were moving parallel to that direction, my wave would also be moving in the same direction. However, this is perpendicular, so I know that if this is my plane of the medium, it's going to be moving in the opposite perpendicular direction, up and down. So what I see here is my last word that I may not know, propagation. Propagation is just going to mean the direction of motion. So if I'm thinking of my transverse wave, I can see it here. This is a little hand, two little fingers holding a slinky. My slinky is making a transverse wave. We see here, we see some hills, some valleys, and we'll talk about what those are called as we get into waves. But we can see that it's moving up and down rather than straight across. So I would be moving my hand back and forth in order to make those waves travel down the slinky. Transverse waves work in that way. Longitudinal is going to be our second type of mechanical wave. Longitudinal waves are also going to oscillate, but in a different way. They're going to oscillate parallel to the propagation. So what that means is, instead of moving my hand back and forth with my slinky to make this shape, instead I'm going to move my hand forward and backwards. It's going to send a wave down the slinky, but the way that the wave travels looks different, right? So a longitudinal wave is going to move down the wave parallel to the direction of movement, rather than perpendicular. My last type of wave is going to be called a surface wave. So the best example of a surface wave is if I were to take a rock and I were to throw it into a lake or a body of water. When it lands, splashes into the water, we know it creates those ripples in the water. That's called a surface wave. This is propagated between two different surfaces, which just means that the two different waves are colliding with one another and they create that ripple effect in the water. Some examples of mechanical waves are going to be water, seismic waves. Seismic waves are what are used to measure earthquakes, and sound waves, which we've already talked about. All three of these are distinctly different from one another, but are all examples of mechanical waves. If you need to pause the video here in order to write this down, please do so. Electromagnetic waves are similar in ways, but definitely different in others. Whereas a mechanical wave needs a medium to travel, electromagnetic waves do not. Electromagnetic waves can travel without a medium. They can carry that energy from place to place without a medium. The best example of this are light waves or visible light. If you've ever watched a movie set in space and you've seen a spaceship fly up and you can see the light waves and then you can hear the noises of the spaceship, that wouldn't really happen in space. You're able to see the light waves, you can see light traveling towards you, but you would be unable to hear the sound waves. You'd be unable to hear those mechanical waves simply because space is a vacuum. There's no air there, there's no medium for the wave to travel through. So the next time you're watching a space movie, think about that. Think about how you'd be able to see the light, you'd be able to see those electromagnetic waves, but you wouldn't be able to see, or you wouldn't be able to hear the sounds of that spaceship or those mechanical waves. Back to electromagnetic waves. They can travel in a vacuum like space. And we've talked about that. They're going to always be transverse. So we see some mechanical waves can be transverse, but they can also be other types of waves. Electromagnetic is going to always be transverse. And we see this model a lot, representative of electromagnetic waves, where we see the electric field and the magnetic field, and they look as if they are parallel to one another, that they're running parallel, or they look like mirrored images of one another. We will continue to explore this, but we want to remember that electromagnetic waves are always transverse. And then some examples of electromagnetic waves are going to be radio waves, kind of looks like a little face, visible light, and X-rays. So again, these three are all very different from one another also. We'll talk about what makes them different as far as frequency and wavelength goes as we continue to explore waves, but this is just our introduction on mechanical and electromagnetic waves. If you need to pause the video in order to be able to write any of this down that you don't have written down, please do so. Have a good day. See you later.